We are going to talk about the basic concept of the integral test. So the integral test, we suppose that f is a continuous, positive, and decreasing function on the interval from 1 to infinity. And we let the an equals to f of n. So what is positive? Positive means the curve of the function is above the x-axis, because as long as the curve is above the x-axis, y is positive, so the function is positive. Continuous means a smooth curve. There is no vertical asymptote. There is no open circle, like a removable discontinuity on the curve. And then decreasing function, that explains everything. The curve is going downhill. So let's take a look at the graph on the right hand side. So we have a blue curve, right? And then what about the pink rectangle? So the pink rectangle, do you still remember when you study integral calculus, the first couple lessons, do you still remember the Riemann sum? So the Riemann sum, before we learn how to use the fundamental theorem of calculus to approximate the area under the curve, we use Riemann sum, right? So the Riemann sum is we use the pink rectangles to estimate the area under the blue curve. So the pink rectangle, has its area, right? So the area is the base. So the base is the width from, so let's save the blue first pink rectangle. We go from 0 to 1. So that is the base. And then the height you have to plug in a point. You have to say when x is equals to 1, do you see that there is a blue point on the curve? So that is the height of the rectangle. So basically every single pink rectangle has its area. You add up all this area, then you get a sum. So the sum is an estimation of the area. But how come the sum of all the pink rectangle is less than the result of the definite integral? Because the sum is an underestimation. So do you see that on top of every pink rectangle, I miss some of the area? So if you add up so many rectangles, there is a underestimation. So that's why the sum of all the a's is less than the result of the definite integral. And another way to say this is the series is trapped under the function. So there is a small underestimation. So that's why the sum must be less than the integral. What about the integral? What kind of integral is this? Do you still remember the improper integral, right? So x goes from 1 to infinity of f of x dx. So when you solve integral in this problem, you better remember how to do improper integral. So that is a definite integral. The lower limit is 1, the upper limit is infinity. So we go from 1 all the way to infinity. What is all the way to infinity? All the way infinity is you look all the way to the right. Do you see that the curve is decreasing? So if you go all the way to the right, is the curve going to approach to 0? If so, maybe on the right hand side, you look all the way to the right. Of course, the screen is not big enough to fit what you want to see on all the way on the right. If the function is so close to 0, so that means the area, those pink rectangles, they are so tiny. Those areas, we don't really care because they are so tiny that it's not going to affect much. That means the sum is pretty much depending on maybe the first couple rectangles, right? The first couple pink rectangles. Okay, so there are two cases. So case 1 is the integral, the result of the integral, the definite integral is a real number. So that means the area, so let's say the area is equals to 10. So 10 is a real number. So since 10 is a real number and the summation, the series is slightly less than the real number, so that means the sum is convergent. So we have a real number. So let's say the real number is 10. We are talking about case 1. You evaluate the definite integral, the result is equals to 10. 10 is a real number. What about the series? The series stands for sum. The sum is less than 10, so that means the sum has to be a real number, and therefore the series converges. All right, and then case 2 is you evaluate the definite integral using improper integral, and the result is equals to infinity. So and also the series is trapped under the function. So due to a little bit of underestimation, the sum is slightly less than the infinity, right? So we have a sum that is slightly less than the infinity. So therefore, we have a sum equals to something slightly less than infinity. Treat that as a smaller infinity, but smaller infinity is still an infinity. So therefore, the series diverges. All right, so that is the integral test. A student asked me this in the past. Hey, let's say the the function is so complicated. For continuous, I can tell that pretty easily. But what about positive and decreasing? If the function is so complicated, I can't graph that in my mind because my brain is not a graphing calculator. Well, if that is the case, then you do have to graph the function to make sure that it's continuous, positive, and decreasing. Usually, when they ask you to perform the integral test, usually, not every single time, maybe sometimes they want to trick you. Usually, they will give you a function that is continuous, positive, and decreasing from 1 to infinity. Usually, they will give you such type of function because in this type of problem, they want you to focus on the integral test. We are not asking you to say, hey, is this continuous? Is this positive? Is this decreasing? No, you do that back in an integral calculus. You don't do that in a series. All right, so that is the basic concept of integral test. If you think my instruction is helpful, please like, subscribe, and share to my channel. Like the videos. What do you think? Let me know in the comment section below. I appreciate your help for watching this. I see you all in the next video. In the next video, I will show you how to perform the integral test. So I will see you all in there. Signing out for now.